Well, hello. Hopefully you're watching these videos back to back, so you didn't have to recall. We were talking. I was just talking because I'm recording these sequentially. We were talking about root mean squared velocity, and so remember velocity can be negative, so you square it to get rid of the negative. You take the average of that. That's the mean, and then you take the square root of it, and it's the peaks from that. And here is the derivation. Root mean squared velocity is 3RT over molecular weight. And what can get confusing for this one is that for the R, you have to use 8.314. So it's a different unit. So 8.314 is joules per mole Kelvin. And there is some physics involved in this. It has to do with units. So we'll talk about it a little bit later. So, and the units are that the joule is a kilogram meter squared per second squared. So the way I don't memorize that. I always think of, so force is mass times acceleration. Acceleration is the second derivative. So if I'm not making any sense, don't worry about it. It's just the way I can reason through it. So uh, displacement. So displacement is just meters. Velocity is the first derivative. That's meter per second, and then acceleration is meters per second squared. So force is mass times acceleration, which is then kilogram meter time divided by second squared. That's what a newton is, and a joule is a newton meter. So then it's kilogram meter squared per second squared. So that's how I derive it in my mind. Okay, so what is the root mean squared velocity of oxygen at 25 degrees Celsius? So let's do this. And one thing to note though, you have to have the mass of the gas in kilograms per mole. I know you're used to 32 grams per mole, but now for oxygen it's 0.032 kilograms per mole. So let's put in the numbers. 3R 8.314 joules per mole Kelvin. Temperature is 298. What am my molecular mass? 0.32 kilograms per mole. And temperature 298 Kelvin. I guess I should go ahead and get rid of the joules and then just put in this kilogram meter squared per second squared. And raising something to the 1/2 power is the same thing as doing the square root. So let us look at the units. So looking at the units here, the Kelvin cancel. I should use red. Kelvins cancel, moles cancel, kilograms cancel, and now we have meter squared per second squared, the square root, which is a meter per second. So our units are in meters per second. That's the reason why we do the this way. It's for the unit's sake. And now we just have to put this in our calculators. And I'll pause for this. And you get 482 meters per second. That's really fast. That's really, really fast. That's half a kilometer in a second. Of course, it's not moving in a straight, well, at least, I mean, it doesn't go continuously for like a whole second. I could, but it'd be very unlikely. That's really fast. I think that's faster than the speed of sound. And I mean, that's just the mean velocity. That means that there's oxygen at this temperature that's moving faster than the speed of sound. Why isn't there a sonic boom everywhere? Well, pressure waves, that's, first of all, oxygen's too tiny. Oxygen's too tiny to create a sonic boom. So you have to have something big, like a bullet or a fighter jet, to create a sonic boom. Also the molecules are what make the pressure waves that sound travels on. So that's why it's not making sonic booms everywhere. And we talked about gases. Some of the mean free path I mentioned is a half a kilometer a second. It wouldn't go that far, uh, just by probability. But the average distance between collisions is the mean free path, and it's usually pretty small. So gases, if you have a container and other gases that go pew 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 pew, they're dancing around everywhere. They're running into each other. It's happens very very quickly. At least at this uh, temperature and pressure. So if you're in deep interstellar intergalactic space, the density of that space is on the order of 3 atoms per cubic meter. So the mean free path can be pretty big for interstellar gas, but not so much for terrestrial. Okay, so the next thing we talk about is a fusion. So let's say that you have a container and you have a hole in a container, and then the gases can slowly go into the other container, and the rate of it is just the speed of one over the speed of other, and the speed is proportional to 1 over the square root of the molecular weight, and that's from the mean free path, or not from the, so the root mean squared velocity, right? So this root mean squared velocity is proportional to 1 over the molecular weight. So which means if you have 2 gases, then you're going to have, so the rate of A over the rate of B is going to be the square root of the molecular weight of the second one over the first. And this, well, if you ever wonder, like every once in a while, you have to fill your tires in your car full of air. Why is that? Well, there's tiny cracks in your tire. It's not a perfect seal. So over time, the gas can seep out of your tires. And like, why don't we put helium in our tires or hydrogen in our tires? You know, well, among other things, it'll escape faster. So that's why we use air and nitrogen. I guess you could use something heavy, but that would last longer. But that's, you know, it's cheaper. Okay, so an unknown gas fuses at a rate that's 0.462 times that of nitrogen gas at the same temperature. Calculate the mass of the unknown. So the rate of A over rate of B is the square root of the molecular weight of B over the square root of the molecular weight of A. So the rate is 0.462 equals the square root of nitrogen gas is 28 grams per mole over X, our unknown. So we square both sides, right? So 0.462 squared. This is 0.213. So 0.213 equals 28 over X. And we can rearrange this. So X equals, I'm basically switching these numbers. So X equals 28 over 0.213. And that's 131 equals 131 grams per mole. So that means that the other gas, this gas A, is likely to be, I would guess it's probably xenon, because xenon has the mass of 131 grams per mole from the periodic table. I mean, it could be something else. I don't know any other gases, just, you know, that's one that pops in my head. So it's probably xenon. Okay, and so why do we care besides unknowns? What will we do? So this is how we enrich uranium. This is one of the ways we can do it. There's another technique that you can use lasers to enrich uranium. But a classic way they do it is to form uranium hexafluoride, also known as yellow cake. And that boils at a much lower temperature. And so then you can boil the uranium hexafluoride and then fuse it Usually they use centrifuges. So heat it up, boil it in a centrifuge, and then over time you can isotopically enrich uranium-235 from uranium-236. Okay, so what do we care? If you dig up uranium from the ground here on Earth, most uranium has is about 0.7% uranium-235 and 99.3% uranium-238. So uranium-235 is the one that can be used as a fuel. So odd number of neutrons in a potentially fissile thing. So uranium-235, uranium-233, but you don't find uranium-233 very much. Usually uranium-235, and plutonium-239. That's typically what we use. You can use plutonium-241, but it's hard to make that pure. Usually you make your plutonium-239. So those are the two isotopes that we use for, I should say nucleotides. Those are the two. They are isotopes. And those are the two nucleotides that we generally use for nuclear fission, and especially in making nuclear bombs. So in civilian power plants, we enrich our uranium to somewhere to 3 to 9% ish, uranium-235. And one of the things with Iran and the nuclear deal that's going on there, they were enriching uranium past 20%, and really that's the only thing they would use that stuff for, is to make nuclear bombs. You're like, how do we know it's not for civilian purposes? There's a couple things you could do with that. You could use it on nuclear submarines. So because in a civilian power plant, the reactive core is huge, but and it's safer that way. Having fuel that's spread out and having a big container, you get less heat in an area, so it's just easier to manage. If you enriched uranium, you would have a smaller reactor, but then it would be more dangerous. It would run hotter, and and the controls have to be tighter. So, like I said, it's more dangerous. So basically, there's no reason why you would do that unless you needed a really small reactor, like something on a nuclear submarine. So, or to make atomic weapons. So, I think the idea was they were probably making atomic weapons. Okay, so how much faster does uranium-235 hexafluoride effuse than uranium-238 hexafluoride? So this is the square root of the mass of B over mass of A. So this is the square root of 238 plus 19 times 6 all over the square root, yeah, that's right. Then 235 plus 19 times 6. So put that in your calculators, your handy dandy calculators. 238 plus, I should put parentheses on this. 238 plus 19 times 6 divided by 235. 19 times 6 and then 2.5. And I should have paused it. Sorry, I should have paused it there. I just had it ready for you, but I did. But you saw me mess up on the previous video, so you know what I do when I'm not talking to you. And the answer is 1.004. It means it's very, very slow. It's really hard to enrich uranium. It's not an easy process. So we try to do it as little as possible to conserve energy. So that's the other thing, is if you enrich uranium past that, it uses a lot of energy. And energy is money. Okay, so let's move away from nuclear politics. and talk about gases. So I told you that an ideal gas, so ideal gas has 22.4 liters at 0 degrees Celsius and 1 atmosphere of pressure. And you can see a couple things that, generally speaking, pressures are slightly different between the gases. And helium is about as close to an ideal gas as can be found. It's not completely ideal, but it's about as close as possible. And why is that? Well, if you remember kinetic molecular theory, that gases have no attraction to each other. So if there is attraction, it seems like the particles are smaller. They join together, and they seem like there are fewer particles than there actually are. The second thing is that the volume has the volume of the gas. If you compress it far enough, the atom's actual size starts to give it a bigger volume than you would think. So so here we go. At high pressure, the volume is higher than predicted. So that's CC. Argon, the ideal gas. Argon's the volume is a little higher, and that is because of the size of the particles. And low temperature, the pressure is lower, and that's because the particles start sticking. So they start sticking together. So that's the non-ideal behavior. And what was done here was then the van der Waals equation. So van der Waals came along and said, well, you know, we can put a correction factor in for this, and we can include that there. And you can see that solving for moles for this is a pain, because you have to do it via an iterative process for solving for n. But here are some of the values for this. There are other ways, there are better ways to do non-ideal behavior. So there's a lump sum approximation called the compressibility factor. So PV equals some fudge factor nRT. That's a very common way to do it. So there's other ways to do it than what's written in this book, and better ways. But that's if you follow us later on. We're going to cover mostly ideal gases, and real gases don't really take into place that much unless you're at a really low temperature or really high pressure, and that's for more industrial processes. And although they show this dramatic shift here in this, it's not really that much at all. I mean, it's very, very small, but at a really high pressure, this can come into effect. So, all right, stopping here for now, and I'll see you when we talk about thermodynamics.